We're excited to be here to talk about like the evolution of Uber search platform. So it's great to meet folks from this community. And later in the talk, you'll see why I'm really excited about this talk and sharing with this community of folks. So to begin with my slides, so this is about myself. I'm a Yupeng Fu. I lead the search platform and also the real-time data platform at Uber. And we bet a lot on the open source technologies, not just for search, but probably many of our key building blocks of our entire tech stack benefit from the open source. For example, I also lead the Kafka, Flink, Pinode for the real-time data. And on the search side, I'm also maintainer of the OpenSearch project and also TSC of the open source software foundation. Later in the talk, I explain why I play this role here. So to begin with, I want to share a few interesting use cases at Uber about where search is used. In fact, search is one of the core functionalities in the applications. So I hope many of you are Uber Eats or Uber Rides customers, and this screenshot is kind of familiar to you. And today we operate globally, and we have more than 1 million restaurants on Uber Eats. And interestingly enough, on each session, the people may actually have access to 1,000 of restaurants or merchants or dishes you can choose from when you open the app or the website. So this is actually a very interesting search problem because we have to predict what the user intent is when they open up the app, and we try to use information from the user's profile, the time of the day. For example, in the morning you may prefer to have some coffee, but later in the evening maybe have some kind of choice for a proper dinner or something. And this is also a pretty complex decision-making problems because they have all kinds of considerations based on the user profile we collect, and also as I listed here, the price, and also the carrier availability, and this is a quite dynamic market. So later in the talk, we will show why the search is quite both interesting and challenging for Uber Eats. I will have a pretty good deep dive on that part. And on the map side, so it also has a very interesting list of search problems. So maybe the moment when you start to use this application on the Uber Rides, you are already interacting with the search platform that we operate. From the place that you can type in some of the characters to try to find the location or destination you want to go to, and then this will do the trigger the backend calls trying to do some autocomplete, but we'll also try to look for from your profile or past search preferences or places to get a desirable location. And when you see the trying to locate the location of the drop-off and also the where to meet the driver, is also an interesting search problem because even for example in this complex, right, for this location, it's a pretty wide range. So depending on your GPS location, we're trying to figure out what's the best meeting spot, because there are also certain policies, regulations that the car cannot stop anywhere on the street. So we have to find the right meeting point where we try to index the geolocations on the map, and we split this into multiple different segments, and then change this to a search and ranking problem, based on both the drivers, the location, the direction they are moving, and also the URL location, and trying to find the closest meeting point for both of the parties. And since we are in the the AI period, so we also invest a lot in the Gen AI and the RAG, and we may notice that actually in the Uber app, for the customer support, We already use a lot of like AI for this purpose, from the chatbots or the automated like the support, ticket creation, like handling. Many of these actually we bet a lot on AI, like for both of the better customer satisfaction, also for the cost efficiency considerations. So this will give a quick overview, and then we'll talk about like, the evolution of the platform or the backend of these applications. So before 2019, I joined around like 2018, and then for several years before that period, like our entire search platform was built on Elasticsearch. So in the early days, Uber's main challenge is actually the scale. It's part of the period where there's like hyper scale like problems. And from on the right side of the chart, you can see the growing numbers of the Uber rides like per day is at the scale of tens of millions, and the scale really, really fast. And this is a great problem for the business, but also a challenging problem for the infrastructure like folks. And we also have another dimension of scaling, which is the number of use cases. So you may know Uber began with like Uber Black, but over the years, you can see we have like multiple like product lines, like for example, like the auto or moto, all the carpool, and on the delivery side, we have food delivery, alcohol, grocery. Like many of them like added like very quickly to open like a new market. So this also translates into a different types of challenges to the platform, which is about like certain features that we need to like support. And in the early days, we operate in the model is more trying to meet the growth of the business growth. And back then, probably the entire team working as like in a SRE mode. So we download Elasticsearch binaries, we deploy inside as clusters, and probably all the team's energy and time was spent on the operations, trying to figure out like, how to grow the cluster size and have a lot of like, best practice to see, probably, for this cluster, there's a like maximum size of each cluster, and how do we like federate those as the data like grows more. And especially for the important use cases, like rides or delivery, we actually put like dedicated clusters for better isolation, and also we extend the white glove support to those like demanding like use cases. So this kind of like kept us like alive for several years. We are lucky enough to sustain this growth until we realized, okay, there are some truly demanding like requests or challenges that we have to think about the technology differently. So the next phase, like from 2019, we started to invest in building in an in-house solution or in-house search engine, like we call like a SEA. So a key motivating use case for this is about our fulfillment matching. So this is actually a core functionality of Uber business that every day, every second, you have a lot of like riders, like click the button, they are requesting a ride, and they want to go somewhere. And in the meantime, on the maps, you have a lot of cars, drivers, like moving in different directions. So this is a real-time search problem. So for people, like if you are familiar with Lucene, like Lucene has this near real-time or NRT, like semantics, that you need to explicitly trigger like a flash to be able to get the latest like updates in your search index. But to us, that we care a lot about like the core latency, because people are waiting, right? The riders, they want to get a ride as soon as possible. In the meantime, we care about the freshness, that we must have like the latest data, because every second we collect the location information from our driver, and driver can move fast, right? Like for example, they can be on the highway every second, they could be like tens of like meters like away. And on top of that, this is also a pretty complex ranking problem, because based on the user profile or the preferences, that there are a lot of rules we have to consider, a lot of factors we have to consider. For example, like the female like rider may prefer female drivers, or there are like budget like users that prefer certain types of cars. So we have to put in a lot of quite like information for us to see how can we do the ranking as fast as possible with like data as fresh as possible. So this triggers us to think, okay, maybe Lucene is not sufficient, and that we indeed like extended like Lucene to build some new data structure. So you can see in this architecture, the server here that has 3 components. So we have a base index concept, we have a snapshot index concept, and we have a live index. So live index here is not Lucene index. Is a data structure that we build in-house that allows like concurrent read and write. We use log-free data structure so that we can take like very high throughput of data writes, at the same time we are able to query them. And this is how we handle the the tail data, like when a lot of appending coming in. And you can see this like data structure kind of like is very memory heavy because we have to allow concurrent read and write, and it cannot be as efficient as Lucene. So periodically, we need to trigger a snapshot that we need to compact this data structure, and we need to convert this into a Lucene document. So this is important because we can free or like release the memory pressure. On downside is like this snapshot index will keep growing because like after compaction and as time goes by, more and more data will come into the snapshot. So then this also go to the bottom layer where it's called as like a base index, because unlike Lucene, which can do the compaction as part of the NRT, that here we have to make like batch like index job. You can see here from this line that our data is from like the source of truth, like could be Hive table, could be MySQL database that like weekly or every like twice a week we need to trigger Spark job, like to rebuild the entire like base index so that we can merge the snapshot and base index into one index to make the index like smaller. Another interesting part on this architecture is that we actually use streaming for ingestion or for data writes. So the updates coming in that does not go to like a push-based like API, like the write API, but instead we publish data into Kafka, and then the server has a Kafka consumer to ingest data from Kafka into the search server or the indexes. So one of the benefits or reason for doing this is that you can see there's like a CS store concept that we try to calculate the delta in the live ingestion pipeline. So to minimize the data we are going to write into the index, which is you can think of as more like a partial update. And another good thing is that writing into a stream actually decouples the producers and the consumers. So that like the consumer or the server that can have is a more sophisticated like like back pressure handling, so that the critical serving query path is not affected by the write path. Or in other words, you can think of when there's like a very heavy ingestion volume coming in without like a streaming based pool-based ingestion, the server can potentially be overwhelmed. But here, because we use Kafka consumer, which itself, we can give the pace control. So this gives a few other good like benefits or from the design consideration perspective. For example, we also use like a gRPC for the communications, unlike the like Elasticsearch, OpenSearch is more like a REST API based. And here we can replicate data to a remote storage, now become like more popular in the cloud native like design. So we probably spent like 1 or 2 years building the system, and then spent another 2 to 3 years to migrate the use cases to the system. And there are some like good learnings actually. So, and also we observed some challenges from like running, operating like a SEA. So despite the fact that the fulfillment or the matching use case that gain a lot from the freshness of this, but we realize, okay, actually many use cases, they do not need real-time like freshness. And this like base snapshot live index data structure introduce quite some complexities. Especially, we cannot directly use Lucene query operator, right? Because we have our own data structure. So for every single Lucene query operator, we have to build an equivalent one, which is federates over the 3 indexes. And in the past few years, for example, in Lucene 9, the vector search or HNSW was introduced. And to support that, we have to build our own version of HNSW algorithm that be able to federate over 3 different indexes. It's a little bit complex graph algorithm, but we made it work. But on the flip side, like it took us 6 months and multiple engineers just to implement this algorithm. Another complexity is coming from the deployment. That I showed in the previous slide. There's a streaming ingestion, so we use Flink for streaming, but the coordination or when we try to make a deployment, especially the breaking changes, is complicated. So we actually use active-passive Flink pipelines, like for this deployment or upgrade purpose, and we have a long like run book for the engineers to follow how to make this like properly. Another challenge is about the ownership, like how we work with our internal customers or stakeholders. Because of this complexity, like we introduced, and also the streaming processing pipelines, it's a bit complex to draw the line between the platform team and also the customer teams. And this results in some certain challenges. For example, okay, there's some components we hard to tell who should maintain that because the template was built by the platform team, but the business logic was introduced by the customer teams. And then over the time, there's some like expertise shifts. So many of us realize, okay, this is hard to maintain. And lastly, on the operational complexity, that because of the base index build concept I mentioned, that it's actually not that straightforward. For people who is familiar with Spark, Spark is when the states become very large, the Spark job can be difficult to maintain or run them like smoothly. Could be like run out of memory, or the school needs like in the executors across different components. So yeah, it's kind of like consume engineers to do that. And that's when we try to search for like what we should do, right? So, and at that time, I actually discovered this amazing talk at this bullying buzzword like 6 years ago, like from like Amazon, like Michael Sokolov and the Candace. They present how the Amazon product search like works. That was truly inspiring, and we found out, oh, this is actually a really cool that we can build a solution like the NRT, just like Amazon. And I know other companies, like for example, Yip also adopted this kind of like paradigm to build their solutions. And this inspired us to build, we call it like Lucene Plus. And on top of what Amazon did, we also try to solve a unique problem, or perhaps like, also common pattern for many other use cases as well, is that in our Uber Eats or delivery, the data model is kind of have this like parent-child like hierarchy, right? You can think of, okay, we have a lot of stores, and the stores can have dishes. Or we can have many like merchants, and these merchants can have like items, right? So pretty natural. And I think like beyond like delivery in other setups, for example, in a forum you can have post can have reply, which is naturally also a parent-child like structure. And for the delivery use cases, we actually can also like model this as a parent-child data set, and we can use the queries is kind of like a join query, which I show like on the left, where people try to find the items or dishes from a restaurant based on some location, like maybe like restaurants close to you, right? And also have some additional like conditions. Hey, I like something like a milk. And on top of that, we also care about like diversity. For example, if we don't like the thing, we want to search like a burger and all the return results or restaurants are McDonald's like all over you, right? So we want to try to have some certain diversity to say, hey, for this category of like, for example, fast food, we probably want to limit this to this like top like at most like 5 are from the top 100, and we want some like healthy food as well. So that's why this diversity like really matters. And if you're familiar with Lucene has two types of join. One is we call this like in just-in-time join, where you need to maintain like the order of the parent and child like relationship, and you ship this like as like multi-docs when you do the ingestion. So this allows very fast like query time like join, but the bad news is that like you cannot change this, or in other words, whenever you change anything in the child structure, you have to resend the entire like parent as a group. And Lucene also has a query time join, which has become more flexible, that can give you like allow different like layout of the index, but it's kind of like less like efficient, right? So here for us, we do have like the need that there will be constant updates coming in, like the dish can become unavailable, new items can be added, and description can change. So we have to have constant updates, but also we want like very fast query time join because we want to have much better like query latency. So this is actually how what we did. That we extended like the Lucene join. We introduced our own parent-child like join operator, and we assume that the index is like well sorted, so that I can see here the stores are sorted like within the city, which makes sense, right? So because you want to find the stores close to you, and also want to sort the items within the store based on some of the scores. Could be like a conversion rate. We want to put the popular items like at the top, and so that like we are able to do some of the fast forward like for early termination. So the trick here is that we keep 3 iterators here. Like one iterator is all the parent, and another iterator is all the eligible parent, which is to say, hey, you have some condition on your parent. It could be, say, the location of this parent should be within this city or given this city ID. And you also have an iterator for eligible child. For example, in my previous example, the child item should have milk as a relevant score. And because I mentioned like we need like some diversity, so for each parent of each store, we probably want to collect top 20. So okay, we'll collect some, and then we're able to fast forward to jump to the next eligible like child operator. So and what we do for the index layout, right? Because it has to be like maintained ordered, and then we realize, oh, the index source is really expensive in Lucene. Like each time you trigger, let's say, a force merge, that's kind of similar to a stop the word like garbage collection in Java. So it takes like minutes to to sort some index. And then it will keep like CPU at like almost 100% for probably several minutes. This is not possible for a serving system. So to address this, we actually adopted the design pattern of the reader-writer separations. So we have the roles of the ingesters. Well, we also have the roles of searchers. So the ingesters actually, we also read from like Kafka, and then we will keep appending this data to the Lucene index, and then periodically we will trigger a force merge to sort all documents in the proper order that we desire. And then we upload this index to the remote storage for the searcher to download and serve. So that means from searcher side, all the indexes they see are properly like sorted, and so that we can run this like fast and efficient like join. But on the ingester side, the dedicated like role is just trying to do ingestion and do the compaction and then do the like sort. We also did some additional interesting more like optimizations. For example, we introduced we call that like a virtual shard like concept that we can allow much higher like parallelism. Okay, let's see. Okay, so like we built this Lucene Plus and we solved the NRT like problems, especially for the delivery, and that's also triggered us to rethink about our strategy, our platform. And for past several years, we have been like in the mode like building like an in-house like solution, which is great like for innovation of like large tech companies like Uber. But also we face constant challenges because the product can become like very demanding. Even though Lucene is great, it's still like a library, right? So it's not like a distributed system. And also we observe that the evolution in the industry and the trend is also very fast moving. Like if you look at the vector search algorithm, after HNSW, there are new innovations like DSN, like quantization. So especially for the past few years, there's also like a heavy adoption of GPU. That's how like NVIDIA build new algorithms can do the efficient vector search on GPUs. So then we realized, okay, just by maintaining and building the system by a team within the company is not scalable enough. So this made us to build like a new strategy, which is we want to collaborate with open source systems that to drive the sustainability and foster the innovation. So sustainability here is actually a keyword that we want to get and benefit from the great contributions from the community, like folks here. And we want to pick industry standard. That's how we pick on like OpenSearch. So last year, around like summer this time, like Uber joined like OpenSearch Software Foundation as a founding member, along with several other companies like AWS and SAP. And we also built a strategic partnership between Uber and AWS on the OpenSearch like development. And we together build the roadmap for this year. And also internally, we invested a lot in adopting this technology inside the company and building the integrations to make OpenSearch fit into Uber. And we also make great extensions, for example, that we build our own like security like plugin, like we made the enhancement to the monitoring, some of those to provide even more finer granular than the default OpenSearch dashboard that can provide. And on top of that, we also want to consolidate or contribute our innovation from our previous generations of systems into OpenSearch. One key innovation we believe is very valuable is this, like we call it like pool-based ingestion. I showed multiple slides that like we can pull the data from Kafka. But OpenSearch or Elasticsearch in the past have been only provide the REST API for people to write into this. And with the pull-based ingestion, you can see we can have much better resiliency to smooth the ingestion spike. So this is one example. You can see, we have a constant public traffic, and then suddenly there's a spike. And in the push-based way, you will see, the system will be overwhelmed and trying to reject this request. It's up to the caller to handle, to do the backoff. And we feel, okay, this complexity can be handled by pull-based ingestion, which is here you can see, there's ingestion lag. And then the system itself will try to catch up as time goes by. And also, this is very useful at Uber for OActive setup, because we found out that this cross-class replication in OpenSearch does not have a sufficient solution or the certain quality for us, which we care about the consistency. So we build the replication at the Kafka layer, which is that the regionally published Kafka can replicate to we call this aggregation Kafka. So this actually, each aggregation Kafka topic has a global view. Then the OpenSearch can just read or pull from this global Kafka topic. Then we have identical views on each cluster, on each region. So we can do the region failover. So we contribute this feature to OpenSearch, and that's already released in the 3.0. And we also build certain extension to this to allow, for example, pause, resume the ingestion, and then you can enable this as easy as add this ingestion config, these parameters. Another extension we made to OpenSearch is to add this gRPC protobuf communication protocol. This also released in the 3.0. Internally, we found it's actually it's quite efficient, and because the gRPC is more modern transportation protocol compared to the previous generation REST and API, that we observe similar performance gains, not just for search but across many other systems at Uber as well. If you're interested, can check this out. That we are keep building extensions on top of that and making new contributions. And we are working on several other very exciting projects as well. I just want to take one as an example that is upcoming this year, that we call this cloud native OpenSearch. So the key idea is that we want to change the OpenSearch architecture from a design that previously optimized for small scale or simple deployments. That's probably 10 years ago how and why Elasticsearch became so popular. It's just hey, it's a single machine deployment, you run it, it works, great, let's add one more node, add more 2 nodes, and then it can scale up. And then if one node is down, it's fine. It have a global state so that you don't worry about the deployment operation. So that was pretty cool for probably 10 years ago. Today, I think in the cloud era where the serverless or the cloud architecture became a norm, that this kind of simplicity may no longer be the primary consideration for a system. And here, especially for us, I operate at a really large scale. We want to optimize for much higher scalability. We want to optimize for the simplicity of the operation that we can do, for example, rolling restart, rolling upgrade without blue-green setup. And so here you can see that we are transitioning the architecture to pull the cluster state out from the nodes previously into etcd. So for people who are familiar with Kubernetes, you can see this paradigm very similar to how Kubernetes works, that you put a Go state in the etcd to say, hey, this is a state the cluster, each node should be in, and then you also collect actual state from each of the node, and then it will try to convert the two. So yeah, we try to adopt the similar like a paradigm, and then we can gradually like change OpenSearch into this like, you know, in our opinion, like more cloud native like fashion. Yeah, so that's pretty much my talk. And thanks for everyone. And then happy to take your questions.
Thank you, Yupeng. I'll see if there are any questions in the online, but before that, let's start with the room. Yeah, I'll go to you. A second.
You talk about like you guys have a parent-child relationship, but let's say that some items at Uber Eats have its description on the option. So let's say that I want to buy a Diet Coke. So you have to find stores that have items that has the option of diet. So how do you guys deal with that kind of parent-child relationship in three, you know, more than just two entities?
Yeah, good question. So today we model as a two level. So we have the store, we have the item, but you have a very good insight. There's also a product concept, which is can be, the Coke can be, you know, a product, and many stores can serve the same like product, and this but have its own like particular like version, which is can be the items. So in fact, that's something like we're working actively with our delivery team to try to make this transition from like the two level hierarchy to the three level. And I think the good news is that like our parent-child like operator actually can be extended to support the multiple levels. As long as your index can be sorted, then we're able to extend the join operator that can understand more than two-level hierarchy.
Thank you. Any other questions in the room? We have time to, I don't know, one more, two questions. Anyone? Okay, let me see if there's anything in the chat. Okay, so big round of applause again to Yupeng. Thank you so much.
Thank you.